Okay, good morning, everyone. Thank you for attending my talk about functional PCA. First, I'm going to tell you about the history of this project. 2 years ago, I was working in one of the projects for the company where I was working, and I was facing the following problem. Sometimes you have data points to use as the input for your machine learning model. But most of the times, you really have functions or sequences. So maybe you have wondering how you can do dimensionality reductions on functions or sequence of numbers. Usually time series, that is the more common that you can find in your daily work as a data scientist. So while I was working on that project and studying a lot about functional data analysis, that I already had a background on that from my physics background, I want to share with you first one of the big conclusions that I found studying functional analysis for data. And it was that the theory of functional PCA is a more general explanation about PCA. That is something that you're going to see in the next slides or at the end of the talk, this big conclusion and the why of that. So let's start to remember how we do the classical PCA. Here you see a plot or a scatter plot about two variables, x and y, that's the classical one, where you can see the midpoint or the mean point, that is the average, and the principal components that are the directions of the most of the variance of the data set. So using those components that are vectors, you can reduce your variables using this matrix operation of the matrix of principal components over the matrix of your data. But there is also an expansion that is not so known for everyone that is called the Carhunel-Love expansion. This comes from some Indian mathematicians where you can do the backward transformation. So from your scores, you can get back your data again. And here we have P that represents the number of variables, in this case is 2, your initial scores, and the principal components that have or explain most of the variance of your data set. So usually you could this whenever you need to reduce the dimensionality of your data set, keeping, for example, 99% of the variance of your data set. But let's go again to talk about what are functional data. This is a more common example right now because of the global warming, where you can see the temperature curves of the surface ocean temperature for almost 44 years. But here, if you are going to use this in a model or a classical machine learning model, you have to transfer this one in just singular data points to introduce that in your model. Here, you can see that we have a domain. So each curve represents a year, and we have the variation of temperature along the months of the year. You can see some oscillation patterns of the temperature, and also you can see that over time, or forward in the years, the temperature is rising. But how you can, again, quantify that structure on the data? So I get very upset with this topic about functional analysis and how to reduce the dimensionality a continuous curve. But first, we have to define or categorize what are the type of functional data. And here I did a more general perspective of this. So the classical one, that is the first scatter plot, you have point data. And a point data have the property that its range is a zero-dimensional range. The next one is the classical functional data set where your domain have a one-dimensional, where your domain have one dimension. And the last one are two-dimensional domain that, for example, is classical in image processing and also in contour maps or heat maps. Here you can see how we can represent functional data for one-dimensional domain using the Carhunen-Loew expansion. So in this case, you can have any set of curves. It could be time series or anything that you want in the domain as the variable. And you have to calculate first the average curve of the data set. And when you solve the problem of the principal components, in this case, you don't get any direction as the classical one. But what you get is the modes of oscillation. That is very similar to something that you can see in any physics course on experimental physics. So here, we have the modes of oscillations that give variation to our data set. And of course, the scores F represents the weight that we gave to each data point or data curve for each component of the system. So to start working with functional data, we have to define how we can represent functional data in a computer. So usually we don't have, or we don't get from the reality continuous data sets. What we have is discrete points for the measuring. For example, in time, we can measure each day or each month or each year. And as you can represent the data set is in the following way. Each row is going to represent a record for the data set. And the index columns represents the time or the index of your domain. Doing this is going to allow you to do an easy working with Python and NumPy in the future. So numerical methods for functional PCA. For this, I'm going to try to reduce this theory about functional analysis to a more easy and understandable expression in matrices. That is going to reduce the problem to something that we usually deal with, that is the eigenvalue problem or eigenequation for matrices and autovectors. So first, you need to understand some main concepts of functional analysis. And I want here just give you a little footnote about this branch of mathematics, and is that if you wanted to understand about quantum computing, it's going to be important to know a little bit or the main concepts about functional analysis. So let's start what is functional analysis. This usually, or it is a branch of mathematics that deals with linear operations of operators or objects over functions. Here you can see the operator B, that is called the covariance operator, that operates on the function C. And it gives a scalar times that function. This is an eigenvalue equation in a more general definition. And the way it operates is through this integral of the product of the covariance operator or function times the function or principal component. Also, in this space, you can define the inner product for functions as you do for vectors. And it's just simple, the integral of the multiplication of the two functions or the components. So we don't have continuous data, but that we really have is discrete information. So we can approximate this using a summation approximation, where here, as you have seen in some of your course on calculus, you can assume a constant time step or domain step and take it out of your summation formula, and you get this one, for example. You can do the same for the condition of orthonormality, that if you have the same functions, it is going to give you, or it is going to return you a 1, and if they are orthonormal, in this case, it is going to give you a 0. And finally, after writing all of this information and approximation, you get this formula. This formula here, that you already know what it is an eigenequation using a matrix representation. So, having this approximation, the first thing that you have to do to the dimensionality reduction of your functional data set in one dimension is to subtract the average mean, the average curve from the data set. Once you have that, you have to calculate this matrix KXX that represents the covariance matrix of your data set. And having that, you have to resolve the problem of eigenvalues for your matrix. You have to take into account here that we are still working with functions, and we are approximating our vectors to behave like functions. So you have to take into account the orthonormality property of our system. So given that we have to accomplish with this orthonormality equal 1, it returns you, or you get to the conclusion that the approximation of our functional principal component is the multiplication of this scalar times the eigenvectors from your matrix eigenequation. So at this point, we have reduced this problem of principal component analysis for functional data to the classical principal component analysis of multivariate data sets. And finally, the transformation for this is very easy. You have, again, to take into account the integral approximation and the scores are the multiplication of these two matrices. X represents your data set of functions, and C is the matrix of the column vectors that represents the principal components. Here again, as the classical problem, you can cut the number of components with the variance that you want to explain from the data set. It could be 90% or 95%, or anything that also allows you to smooth your data set to get the principal pattern behind that. Okay, at this point of the process in my research about that problem, I get obsessed with that and I say, okay, and how you can do it with multivariable or with many variables? How we can write this set of equations in an easy way again to solve the problem and get also the joint pattern of variation between variables, because that's what you're going to find in reality. You are going to find not just independent functional variables in data science, but you are going to find correlated variables in data science. So I remember from my physics classes in quantum physics that we were dealing with block matrices. So that's a very nice topic, and I remember about that, and I say, okay, I can write this problem again, but using block structure. So I created an N matrix that is just the concatenation of your three component variables, X, Y, and Z. And if you take a piece of paper, and as you say in Colombia here, hacen un poco de boleo con el lápiz, you can get to this interesting property, that is that the covariance of these two data matrices have this symmetry property that the covariance in the different order is equal to the transpose. And here, you can see our final matrix using this property of symmetry that is also a generalization of your simple data points, because the transpose of a real number is itself, but it also generalizes to matrices in this case. So having this, maybe you can see that we can solve the problem again using what we already know from our basic understanding of data science for PCA. So I have again my problem of my equation of eigenvalues, but the difference is that the autovectors that the computer is going to return to me have a block structure. The first part is going to represent the autovector for the x variable, the second one, the eigenvector for the y variable, and the last one, the eigenvector for c. And you can do this with any number of variables that you want. And again, you have to get the approximation of the principal component function of this scalar times the autovector. And in general, from the Carhunen-Loew expansion, you can write a multivariable data set in this way, where you can analyze that if you do the principal component analysis just for univariate method, one by one, you are going to get different scores, values. But in this case, when you do the multivariate, you are going to the same scores for each of the components of the variables. So this is the part that is very interesting and very, very nice to do. That is, take this implementation into NumPy. And this is one of the part of the history of this project that, okay, I was in my work on the company and we found different third-party libraries that you can use to implement this multivariate functional PCA, but usually they come from research groups, and if you see that from the production perspective of your system in the company, it is going to be very unstable. The first thing is that you are going to deal with the versions of different packages, and this is going to make very hard the installation for the other people in the team. So here I was challenged to, okay, I know a little bit, no, I know something about this, I can research about it, and I'm going to find a better way to implement the in-house library or package for functional multivariate PCA. So, but we need any real data set to test my library or to start implementing my library. So this is the case, the classic data set that you are going to find in any book of functional data analysis, and is the J cycle. It's just a measure of how people work. It measures the angle of the knee and also the femur relative to your rest of your body. So that's why you have two variables, for the knee and for the hip. And they are also correlated, as I told you about the real data sets. So after working on that and doing my block matrices framework, for example, and going to NumPy and find the right functions to write this, it ended that I needed just 20 lines of code to implement this analysis. So here I put this in order with the equations to see how you can implement that. So for example, NumPy have this method that is called block, where you can put your functional data set just as a block, and you can put any number of variables that you, any that you want, also keeping in mind the the capability of the RAM memory of your computer. For example, you can 10 or 20. Here, you do what is classical in this line, and is solving the eigenvalue problem of this covariance matrix. And finally, you have to also keep in mind that you need to calculate the mean curve for the data set in order to transfer your data set to the scores. And this is a very important step, and where this you have to think about what you want to predict and what the math of this means. As you see here, we are having the variation relative to the mean curve. So the mean curve has to be kept from the trained data for future predictions or future transformations. If you don't do that, you are going to having the wrong scores for your data set or for your test or prediction data set. So you can test how good this transformation is doing the approximation of any of the function using, again, the Carhunen-Loeff approximation, where P is where you put the number of principal components that you want, and using this matrix. And here you can see that is very close, the real curve, to the approximation from the Carhunen-Loeff expansion. And also, you can plot more interesting things, that is to see the variation of one of the principal components around the mean curve. Here the plus is the mean curve plus the first component of this variable. I think that here is the ni. And the minus is just subtracting that component to the mean. And also you can plot in a multivariate way where you can see the cycle of walking and that it is close, and how is any of the components giving variation to the way people walk. And again, I get more upset with this. And okay, now I wanted to find a way of how to create synthetic data and also create correlated synthetic data. So I went to any of my books about stochastic processes, and I found something very interesting, and it's that an arithmetic Brownian motion or random walk that is continuous in time, Wiener have found a way to represent that process using the Fourier expansion. So in this case, the sin functions represent our principal components, and f represent the scores of our system. The mean curve is going to be 0, as any Gaussian process, or white noise process, and you can check if this formula is true. For example, using the 10 first components, you get this blue line, okay? This is not still a random walk. Then you try with 100, and it looks better. And when you try with 1,000, it is very similar to a random walk. You can build a set, for example, of 100 paths of the Wiener process. And here you can see something interesting that is, okay, this have the diffusion property of the random walks. And you can do the same implementation of Python and see if it returns, or check if it returns these same functions for your synthetic data set and the same scores. Just a way of testing it. And also I was feeling very curious about how to go beyond in that. But as I told you, I wanted, okay, in real life we have correlated data, how we can create correlated data. So searching in some papers, some people that write about Carhumane law of expansion, I found an Indian guy with a PhD thesis where he explained how to correlate two functional data sets from two uncorrelated Brownian processes. In this case, X and Y. Here, rho represents the correlation. In this case, I use 0.8 to perform this transformation where X prima and Y prima are the correlated functions. So here, in this plot of the covariance matrix, you can see the data set or the covariance before the correlation and after the operation of correlation. Here it's interesting that you can see again the block structure of the problem, where the off-diagonal right now have a lighter color that represents that we have introduced a correlation in our data set. And again, you can do the principal component analysis of the variation. Here you have the mean curve, and the plus and the minus. And also you can see here the cycle that we have in this case. That is not a closed cycle because we are talking about a Brownian process that have a diffusion property. That's why you see this end of each curve that is going to be to separate. And as the conclusions of this work that I will share with you is that when I was working with this model or this transformation, okay, we were using a random forest for the prediction of the model, but I found that it doesn't have any difference to use the univariate principal components analysis versus the multivariate principal component analysis. And the reason is that because random forests are models that have the property to deal with nonlinear relationships, it doesn't matter if you do the multivariate or univariate, because the multivariate, as you know, it returns uncorrelated scores or an uncorrelated data set that you can use mainly in a linear model to avoid any collinearity issues. And the last one that is very important and is that, okay, you can deal with fancy maths, like in this case, any very complicated model, but you also have to understand the business that you are dealing with. So in this case, or in that case, I was dealing with time series data sets where I wanted, in the view of finance, to see how each individual curve is going to grow. But in this case of functional data analysis, the scores doesn't return you information about how each individual curve is going to grow. It returns information about how it varies relative to the mean curve. So you have to be very careful with that because it could give you the wrong prediction that you want for your business in this case. Also, I wanted to put a last one, but and it's about that it's like a kind of embedding, yeah, but it's just linear, but I have to read more about what right now embedding and generative AI models work with. I think that they are more complex and they have no linear transformation inside, but it's a kind of the same thing that we are talking about here, because you can take image where you have the value of the pixels in a two-dimensional domain and do also functional multivariate PCA for this and get an scores and then reconstruct the image again using those scores with the Carhumane law of expansion. And this is some of the reference that I use for this research. Also at the beginning of the presentation, there is a link to my blog where I put more details about this work and this research about functional analysis. And thank you for your time.